About 5.8 billion light-years away, deep within the Phoenix constellation, there exists a true cosmic monster, Phoenix Asterisk. This is not an ordinary black hole. It is one of the most massive and terrifying objects the universe has ever created. A supermassive black hole with an estimated mass of up to 100 billion times that of the Sun. Here, all familiar laws of physics seem to bend. Time slows down. Space is torn apart. Phoenix Asterisk does not merely consume matter, it is the end point of everything. And today, we will look directly into the face of the greatest darkness humanity has ever known. Phoenix A star is a supermassive black hole located at the very center of the Phoenix cluster, one of the most massive and luminous galaxy clusters ever discovered. This is not a typical group of galaxies. The Phoenix cluster is a colossal structure where immense gravity binds thousands of galaxies together. At the very core of this system, Phoenix A star exists as a dark heart, silently controlling everything around it. This galaxy cluster is named after the mythical phoenix, a symbol of rebirth, and the name is entirely fitting. This is one of the very few places in the universe where enormous streams of cold gas continuously flow toward the center. Thanks to this abundant supply of material, the star formation rate here reaches a record-breaking level, about 740 solar masses per year, equivalent to hundreds of new stars being born continuously, far exceeding the rate in our Milky Way by hundreds of times. Right beside a gigantic black hole capable of devouring everything exists an unprecedentedly powerful star factory. To grasp the sheer scale of Phoenix A, consider our solar system. If the Sun were a grain of sand, Phoenix A would be an enormous mountain. Its event horizon, the boundary beyond which not even light can escape, extends up to 590 billion kilometers. This number is so vast that light would take weeks just to travel across its diameter. According to conventional understanding, massive black holes typically emit enough energy to suppress star formation. But in the Phoenix cluster, that rule appears to be broken. Phoenix A star lies about 5.8 billion light-years from Earth. This means the light we observe today left it at a time when Earth had not even formed yet. To put this into perspective, light takes about 100,000 years to cross the Milky Way, but to reach the Phoenix cluster, it must travel for nearly half the age of the entire universe. Even if you could move at the speed of light, the ultimate limit of nature, by the time you arrived, our sun might have long since aged or faded away. However, what makes Phoenix A star truly terrifying is not just its distance, but its immense size. This black hole has an estimated mass of 100 billion times that of the Sun. The diameter of its event horizon, the boundary from which even light cannot escape, reaches approximately 590 billion kilometers. For comparison, the distance from the Sun to Pluto is only about 5.9 billion kilometers. That means Phoenix A star is nearly 100 times larger than the entire span of our solar system. If it replaced the Sun, every planet, from Mercury and Earth all the way out to the distant Oort cloud, would lie deep within that dark event horizon. There would be absolutely no chance of escape. Even traveling at the speed of light, it would take about 71 days just to complete one orbit around its event horizon. Its gravitational influence extends across dozens of light years, enough to dominate the motion of nearby stars. Phoenix A star is not a quiet entity. It constantly feeds on surrounding gas and matter, forming an ultra-hot accretion disk with temperatures reaching millions of degrees. From this region, it launches powerful jets of matter at speeds approaching the speed of light, piercing through intergalactic space and turning its surroundings into a colossal cosmic furnace. So the biggest question arises: how can a gigantic black hole like Phoenix A star even exist? The universe is only 13.8 billion years old. At normal growth rates, no black hole should be able to reach 100 billion times the mass of the Sun in such a relatively short time. The main reason lies in the Eddington limit, a crucial physical barrier. When matter falls into a black hole, it is heated to millions of degrees and emits extremely intense radiation. This radiation creates an outward pressure, like a safety valve, preventing the black hole from feeding too quickly. In other words, the faster a black hole consumes matter, the more it limits itself. And yet, Phoenix A star seems to have completely broken this rule. As a result, scientists have proposed several powerful hypotheses to explain it. One possibility is that Phoenix A star did not form from the death of a star like typical black holes. Instead, in the early universe, a massive gas cloud may have collapsed directly, forming an enormous black hole from the very beginning, completely bypassing the gradual growth phase. Another hypothesis suggests that Phoenix A star was not born massive, but grew over time. Initially, it may have just been a small black hole. However, through a series of collisions and mergers with other black holes, combined with continuously feeding on surrounding matter at an extremely high rate, it gradually became a giant. This process may have occurred in a uniquely chaotic environment that scientists still do not fully understand today. For decades, Tone 618 was considered one of the largest known black holes, with a mass of about 66 billion times that of the Sun. At that scale, it essentially defined the upper limit of supermassive black holes, a symbol of the universe's extremes. However, the discovery of Phoenix A star has completely changed that picture. With an estimated mass of up to 100 billion solar masses, Phoenix A star clearly surpasses Tone 618. It is not just larger, it sets a new benchmark for what a black hole can become. The difference lies not only in size, but also in activity. Tone 618 was observed as an intensely luminous object in the past, but today shows signs of reduced activity. Meanwhile, Phoenix A star sits at the center of a matter-rich galaxy cluster and is still in a phase of rapid growth. It continuously pulls in gas and surrounding matter, forming an ultra-hot accretion disk that emits high-energy radiation. At the same time, massive jets of matter are launched from its poles at speeds approaching the speed of light, directly impacting the environment of the entire galaxy cluster. At this scale, Phoenix A star is not just an isolated black hole. It is a gravitational center capable of influencing the evolution of trillions of stars around it. What would happen if our solar system accidentally entered the sphere of influence of Phoenix A star? Everything would be destroyed gradually from the outside inward. At the outer edges, planets like Jupiter and Saturn would be the first victims. Surrounding the black hole is an ultra-hot ring of matter emitting intense radiation, powerful enough to strip away their thick atmospheres and vaporize distant icy rings. As the solar system moves closer, the immense gravity of Phoenix A star begins to show its true power. It pulls planets out of their stable orbits. Some may collide with each other, while others are flung out into space. The once orderly system would turn into a chaotic region filled with violent collisions. A horrifying phenomenon known as spaghettification would occur. The sun would be stretched into a stream of superheated plasma. The remaining planets would suffer the same fate, crushed into dust and gas, stretched into enormous streams of matter. Eventually, everything left of the solar system would fall inside the black hole's event horizon. This is the boundary beyond which nothing can escape, not even light. But the universe is not only filled with black holes that consume everything. In Einstein's equations, scientists have also found a completely opposite concept: white holes. If black holes pull everything in and let nothing escape, white holes do the reverse. They allow no matter to enter, but continuously eject matter, energy, and light outward. You can imagine them as a giant cosmic fountain. Some scientists suggest that black holes and white holes could be connected by a space-time tunnel known as a wormhole. If Phoenix A star were to encounter a white hole, what would happen? In one scenario, the two could form a temporary balance. The white hole continuously ejects enormous amounts of matter and energy, while Phoenix A star immediately absorbs it all. The result would be an extremely chaotic region of space where gravity and energy collide violently, releasing tremendous radiation that could affect a vast area of the universe. Another possibility is the formation of a wormhole. Phoenix A star would act as the entrance, while the white hole serves as the exit. Matter could travel from one place to another almost instantly. However, such tunnels would be extremely unstable and could collapse at any moment, causing catastrophic consequences. But the most likely outcome is that the white hole would quickly be destroyed. When approaching a massive black hole like Phoenix A star, a white hole would eventually be torn apart and consumed. All the matter it ejects would become fuel for the black hole, making Phoenix A star even larger and more powerful. No matter which scenario occurs, it would remain one of the most violent and mysterious phenomena in the universe, where the familiar laws of physics may be completely broken.